Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
So, right now, there is a number, and I mean a genuinely massive, incredibly fundamentally valuable number, that simply possessing it on your hard drive without permission has actually been considered a federal crime.
Yeah, which just sounds completely like science fiction, but it is a very real consequence of how our digital infrastructure is built. Because, we tend to view numbers as just mundane counting tools.
Right, like tally marks or something.
Exactly. But a very specific subset of them are essentially the load-bearing pillars of global security.
Which completely flips how you think about everyday math. And for you listening, we're going to break all of that down today. Since I am playing the student today and you are the lecturer, my job is to ask the questions that help our listener extract the absolute best insights. I'm going to push back and ask the why questions.
I love it. I'm officially ready for the lecture hall role. We really have a lot of complex, fascinating ground to cover. And, well, breaking down the hidden architecture of these concepts is what we are here to do.
Let's get into it. So today, our source material is section 3.1 of chapter 3 from Contemporary Mathematics. And the mission for this deep dive is exploring prime and composite numbers.
Right, but we aren't just memorizing textbook definitions here.
No, not at all. We are looking at the mechanics of why these numbers literally rule the universe from, ancient history all the way to modern cybersecurity. So whether you are trying to prep for a math class or you are just insanely curious about how online banking stays secure, this deep dive is going to completely change how you view everyday numbers.
Absolutely. And to understand the illegal numbers, we first really have to understand the sandbox we're operating in. So section 3.1 grounds us in the integers.
Those are whole numbers.
Right, exactly. We're dealing with whole numbers. The natural counting numbers like 1, 2, 3, and the integers, which add 0 and the negative numbers into the mix. And the fundamental operation when you are working with integers is divisibility.
Which is just figuring out if one integer can be divided by another without leaving any kind of remainder, right?
Spot on.
But wait, before we break numbers apart, how do we know if one number easily fits into another? I mean, without just doing long division for 10 minutes.
Well, divisibility rules are those shortcuts we all learn in grade school. Like, if a number ends in an even digit, it's divisible by 2.
Right, or if it ends in a 0 or a 5, it's divisible by 5.
Yeah, those are the visual ones. But the textbook gives us some incredibly clever diagnostic tools for other numbers. For example, to check if a massive string of digits is divisible by 3, you don't actually divide the whole thing, you just add up its individual digits.
Right, just the digits themselves.
Just the digits. If that sum is divisible by 3, the entire original number is 2. And the same exact rule applies to checking if a number is divisible by 9. Add the digits, check the sum.
Okay, let's unpack this. Because I learned that trick years ago, but it always just felt like a magic parlor trick. Why does adding the digits of a number have absolutely anything to do with its divisibility by 3 or 9? Like, what is the actual mechanism there?
It's actually really elegant. It comes down to the fact that we operate in a base 10 number system. So let's take a small number, like 21. In base 10, 21 is actually 2 groups of 10 plus 1.
2 times 10 plus 1. Got it.
Now think about the number 10 in relation to 9. 10 is just 9 plus 1. So any group of 10 can be thought of as a group of 9 plus a little leftover piece of 1.
Oh, I see where this is going. If I have 2 10s, I actually have 2 9s plus 2 little leftover ones.
Bingo. The 9s part is obviously perfectly divisible by 3 and by 9, so you can completely ignore it.
Wow, okay.
Yeah, all you are left with is the leftovers. The 2 leftover ones from your 10s place, plus the one you already had in the 1s place. 2 plus 1 is 3. You are literally just adding up the leftovers.
That is brilliant. You are stripping away all the guaranteed multiples of 9 and just looking at the remainders. So if the remainders add up to a multiple of 3, the whole massive number fits cleanly into 3.
It is a beautiful mathematical mechanism, isn't it? Yeah. And there's another great shortcut for the number 4. You don't have to add anything. You just look at the very last 2 digits of a massive number.
It's just the last 2.
Yep. If those last 2 digits form a number divisible by 4, the entire giant string is divisible by 4.
Let me guess the mechanism here. It's because 4 goes into 100 perfectly, 25 times. So anything in the hundreds place or the thousands or millions, it's already guaranteed to be divisible by 4.
You've got exactly. You only have to check the tens and ones place because everything larger than that is already a perfect multiple of 100.
Man, it's all about finding shortcuts to see if things fit together perfectly. And, the textbook gives a really grounded example for why we even care about this harmony in the real world.
It's a preschool teacher example, right?
Yeah, Francis. So Francis is a preschool teacher. He has 15 students and 225 sheets of construction paper.
Yeah.
And he just wants to know if he can distribute the paper equally without any leftovers. I mean, divisibility is fundamentally about fairness. It's about knowing if you can create equal groups without anyone getting shortchanged.
Distribution and harmony in quantities. And Francis just needs to know if 225 is divisible by 15, which, spoiler alert, it is.
Yeah, each kid gets 15 sheets.
Right. But while finding numbers that divide perfectly is very useful for preschool teachers and logisticians and engineers, the irony of modern mathematics is that our entire digital world isn't built on numbers that divide cleanly.
No.
No, it's built on the rebels, the numbers that absolutely refuse to be divided by anything but themselves.
Ah, the prime numbers.
Yes, so a prime number is a natural number greater than one that has exactly 2 unique divisors, the number 1 and itself.
Like the number 7.
Exactly. You can't divide 7 evenly by 2, 3, 4, 5, or 6. It's just a mathematical dead end. Same with 19. But if a number has more than 2 unique divisors, like 4, which is divisible by 1, 2, and 4, or 26, it is called a composite number.
Because it's composed of other smaller integers.
Precisely. And we should note the special rule here, which is that the number 1 is neither prime nor composite. It's its own unique thing.
Right. So establishing if a tiny number like 19 is prime is obviously easy. But the textbook gets into checking massive numbers.
Mm-hmm.
And if I have a target number in, say, the tens of thousands, I would logically assume I need to test every single number up to half of its value. Because clearly a number can't have a whole divisor larger than half of itself.
That is a very common assumption, and it makes sense intuitively, but it would waste an enormous amount of computing power. The textbook offers a mathematical shortcut.
Okay, I love a shortcut.
You don't have to test divisors up to half the number. You actually only need to check prime divisors up to the square root of the number you are testing.
Wait, why stop at the square root? You are leaving out a huge chunk of potential divisors.
Because factors always, without exception, come in pairs. Let's look at the mechanics of the number 36. The square root of 36 is 6.
Okay.
Let's list the factor pairs. 1 and 36, 2 and 18, 3 and 12, 4 and 9, and finally the pivot point 6 and 6.
Oh, I see. Every time the first number in the pair gets larger, the second number in the pair gets smaller.
Exactly. If 36 had a factor larger than 6, which it does, like 9, its partner in the pair absolutely must be smaller than 6. In this case, 4.
Right.
So if we haven't found a factor by the time we hit the square root pivot point, we aren't going to find one at all because we already checked all the possible small partners.
Wow, that drastically shrinks the workload. The text uses the example of 2,117. The square root is roughly 46. So instead of checking 1,000 different numbers, you literally only have to check the handful of prime numbers up to 46.
Exactly. If none of those fit, it is definitively prime.
It is an incredibly efficient algorithm. But here's where it gets really interesting. Because we need that efficiency. Finding giant prime numbers is an absolute obsession in the modern world. Section 3.1 pivots here into the application of primes and encryption.
High-stakes stuff.
Yeah, the fact that every single time you buy something online or every time you send a secure message, your privacy relies on composite numbers made from multiplying 2 incredibly massive prime numbers together.
That's the bedrock of digital security.
But I really want to talk about the why here. If computers can multiply 22 million digit numbers in a fraction of a millisecond, why is it so impossibly hard to do the math in reverse?
Well, what you are describing is called a trapdoor function. It is a mathematical process that is incredibly easy to do in one direction, but practically impossible to reverse without a specific key.
It makes me think of mixing paint. Like if I take a very specific bucket of yellow paint and mix it with a specific bucket of blue paint, I can create a unique shade of green in about 5 seconds. But if I hand you that bucket of mixed green paint and say, extract the exact original yellow and blue, you can't do it. The information is permanently tangled.
That is a perfect physical analogy for the mathematics of RSA encryption. When a computer multiplies two 200-digit prime numbers together, it creates a 400-digit composite number. Doing the multiplication takes no effort at all.
Just a millisecond.
Right. But if a hacker intercepts that 400-digit composite number, they have to figure out which two specific primes created it. They basically have to unmix the paint.
Because those original primes are the literal keys to decrypt the data.
Yes. And because prime numbers have no pattern, they don't follow a predictable formula, the hacker's computer just has to guess and check. It has to try dividing that massive composite number by every single prime number that exists up to its square root.
Which brings us to the staggering reality the text points out. Some of the prime numbers used for this are so massive that to reverse engineer the composite number and find the two primes, it would take a modern computer 300 trillion years of guessing and checking.
This raises an important question: just how valuable are these numbers?
Yeah.
Because the asymmetry of the computation is what keeps your bank account safe. Multiplying takes a millisecond. Factoring takes longer than the lifespan of the universe.
Which brings me back to the hook we started with, because I was reading the Who Knew sidebar in the textbook, and it mentions illegal primes. And my first thought was, wait, how can a math concept be illegal?
Right, sounds absurd. But because these large primes are the physical keys to secure software, they have immense commercial value. They literally become the intellectual property of security companies.
So a number gets copyrighted.
Essentially, yes. In the early 2000s, DVD encryption was cracked using a specific algorithm, and someone realized that the computer code to crack the encryption could be mathematically represented as one giant 1,400-digit prime number.
Wait, so the prime number itself literally was the computer code?
Yes. It translated directly into the executable code. And because distributing the copyright-breaking code was illegal under the Digital Millennium Copyright Act, distributing that specific 1,400-digit prime number became illegal. At least one prime number was actually declared contraband to protect that property.
You could theoretically print this number on a T-shirt, and wearing the T-shirt would be a violation of federal law.
Exact.
That completely reframes history for me. Because if these structural dead ends, these primes, are this powerful today, it makes total sense that brilliant mathematical minds have been obsessed with them for centuries. I mean, long before computers or digital encryption even existed.
They were studying the underlying architecture of the universe without even knowing what it would eventually be used for.
Exactly.
If we connect this to the bigger picture, the history of mathematics is full of people who were captivated by the pure puzzle of primes. The textbook introduces us to a few of these figures who saw the world completely differently, and one of the most inspiring is Sophie Germain.
Oh, she's amazing. Born in France in 1776, right?
Yeah, right, into a wealthy family. She fell in love with number theory by hiding in her father's library during the French Revolution.
But because she was a woman in the 18th century, she was explicitly barred from attending college. Like, she couldn't go to the École Polytechnique in Paris.
She refused to let that stop her, though. She studied clandestinely. She got her hands on university lecture notes through friends, and she actually began submitting brilliant mathematical proofs under a male pseudonym.
Monsieur Leblanc, right?
Yes, Monsieur Leblanc. She even corresponded with Carl Friedrich Gauss, one of the most famous mathematicians in history, under this fake name. And Gauss was astounded by her brilliance. When he finally discovered she was a woman, he was deeply impressed by her incredible tenacity.
And she left a massive legacy in the field of number theory, the Sophie Germain primes.
Yes, a very specific structural relationship.
The textbook defines a Sophie Germain prime as a prime number, let's call it P-Eulers, that can be plugged into a very specific formula, 2 times P-Eulers plus 1. If the result of that formula is also a prime number, then the original number today is a Sophie Germain prime.
Let's run the mechanics on that. Take the prime number 23.
Okay, 2 times 23 is 46, plus 1 is 47.
Right. And 47 is also a prime number. Therefore, 23 is a Sophie Germain prime.
It shows a structural relationship between primes. They aren't just random. There are these beautiful hidden pathways connecting them. And ironically, Sophie Germain primes are highly sought after in modern cryptography today to create what are called safe primes.
Which is incredible. She was doing the math in the 1700s that secures our servers today.
It really highlights the timelessness of the math. And the textbook also brings up another incredible figure from section 3.1, Srinivasa Ramanujan.
Yes, born in 1887 in southern India, he was a completely self-taught mathematician.
He literally just started working through a 2-volume textbook of theorems while in high school and ended up making these massive intuitive leaps in the study of the distribution of primes.
The story the text includes about him perfectly captures how differently he perceived the integer sandbox. So Ramanujan eventually came to Cambridge to work with the famous British mathematician G.H. Hardy. And one day, Hardy went to visit Ramanujan in the hospital.
Okay.
Hardy mentioned that he'd arrived in a taxicab with the number 1,729, and Hardy casually complained that it felt like a rather dull, uninteresting number, and he hoped it wasn't a bad omen.
And Ramanujan instantly, from his hospital bed, says, "No, Hardy, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways."
Just right off the top of his head, he knew immediately that 1 cubed plus 12 cubed equals 1,729. And he also knew that 9 cubed plus 10 cubed equals 1,729.
It's an astonishing level of intuitive recall. I mean, to me, or to Hardy, 1,729 is just a quantity, a magnitude. But to Ramanujan, integers had unique personalities. They had internal structures. It's almost like they had their own DNA.
DNA is a really great way to look at it, because building on that idea of internal structure, the textbook introduces us to how we can extract the genetic makeup of any composite number. This is the most powerful tool in section 3.1, the fundamental theorem of arithmetic,
Which states that every single natural number greater than 1 can be expressed in exactly one unique way as a product of primes.
Right. If you break any composite number down far enough, you will always hit a foundational layer of prime numbers multiplied together.
It's exactly like the periodic table of elements. Oxygen and hydrogen are prime. They are fundamental elements. You cannot break them down chemically into simpler substances, but water, H2O, is a composite molecule. You can break it apart.
Right, into hydrogen and oxygen.
Exactly. And just like water is always exactly 2 hydrogens and 1 oxygen, every single composite number has a unique chemical formula made entirely of primes.
That is a flawless analogy. The primes are the elemental atoms of mathematics. And to find a number's chemical formula, we use a mechanical tool called a factor tree.
Which is literally just branching down until you only have prime leaves.
Exactly. You write your composite number at the top. Let's take the number 80. You draw 2 branches down to any 2 whole factors of 80. Let's say 8 and 10.
But neither 8 nor 10 are primes, so the molecule isn't fully broken down yet. We keep branching.
Right. The 8 branches down to 2 and 4. Now, the 2 is a prime number. It's an atom, so that branch stops. It becomes a leaf on our tree.
And the 4 branches again into 2 and 2. Those are prime leaves.
Exactly. Now we go back to the 10 from our first branch. 10 breaks down into 2 and 5. Both of those are prime leaves.
So if we gather up all the prime atoms at the ends of our branches, we have 4 2s and 1 5. 2 times 2 times 2 times 2 times 5 equals 80.
Perfect. And because mathematicians love efficiency, instead of writing out 4 2s, we use the shorthand of base and exponent notation from the textbook. We write 2 to the 4th power times 5.
Where the 2 is the base and the 4 is the exponent, telling us how many times to multiply the base by itself.
Right. What's fascinating here is that this prime factorization, 2 to the 4th times 5, is a completely unique fingerprint for every single number. There are no 2 numbers with the same prime factorization.
So what does this all mean? Now that we have these prime fingerprints, how do they actually help you in the real world? Like, what is the practical application?
Well, it gives us incredibly precise tools for organizing space and time, specifically through 2 concepts, the greatest common divisor and the least common multiple. Let's start with the greatest common divisor, or GCD.
Which is the largest divisor that 2 or more numbers share.
Exactly. And because we know how to find the prime elements of numbers, we can find the GCD by just comparing their chemical formulas and pulling out the atoms they have in common. The textbook gives a great practical example. Imagine you are putting down floor tiles.
Cool.
Your room is 570 centimeters wide and 450 centimeters long. You want to use the largest square tiles possible without having to cut a single tile.
So you need a number that perfectly divides both 570 and 450. You are looking for their greatest common divisor.
Right. So we build the factor trees. 450 breaks down into 2 times 3 squared times 5 squared. That's its chemical formula.
And 570 breaks down into 2 times 3 times 5 times 19.
Now, look at what elements they share. They both have at least 1, 2. They both have at least 1, 3. And they both have at least 1, 5.
But they don't share the 19, so we just throw that out.
Exactly. We just multiply the shared atoms together. 2 times 3 is 6. 6 times 5 is 30. The greatest common divisor is 30.
Wow, okay. So you need to buy 30 centimeter square tiles, and they will perfectly cover the 570 by 450 room without a single millimeter of waste.
It's extremely practical.
Yeah, and you could use the exact same mechanism for the textbook's bookshelf example. Like, say you have 24 sci-fi books, 42 fantasy books, and 30 horror books. And you want every shelf to have the exact same number of books, but no mixing genres. You just find the GCD of those three numbers, and it tells you the optimal shelf size to divide everything equitably without leftovers.
The GCD is all about dividing physical space or quantities perfectly, but then the text flips the concept to look at time and synchronization, using the least common multiple, or LCM.
Which is the smallest positive multiple that a set of numbers shares. Because the flip side of a divisor is a multiple, right? Like 5 divides into 45, so 45 is a multiple of 5.
Right. Where the GCD divides, the LCM synchronizes. It tells us when different independent cycles will overlap.
Oh, like when processes line up. The textbook gives that simple example of two students, Joao and Amelia, who volunteer to the facility. Joao goes every 6 days, Amelia goes every 10 days.
Right. So if they both volunteer today, when will they see each other again? You just find the least common multiple of 6 and 10. The multiples of 6 are 6, 12, 18, 24, 30. And the multiples of 10 are 10, 20, 30.
The smallest number they share is 30. They will sync up in exactly 30 days.
And the beauty of this math is that it scales up from a volunteer schedule to the cosmos. The text points out that Venus orbits the sun every 255 days. Jupiter takes 4,330 days. Finding the least common multiple of those two large numbers tells astronomers the precise number of days until those two planets hit the exact same alignment again.
That is just wild. It is the invisible architecture of the universe. I mean, from dividing construction paper in preschool to calculating planetary orbits.
It really is.
So, to recap the journey for you today, we moved past simple arithmetic to understand divisibility through the mechanics of base 10. We found the prime numbers, those mathematical atoms that refuse to be broken down. We explored the trapdoor functions that make prime multiplication instantaneous, but prime factorization take 300 trillion years.
The 300 trillion year encryption.
Right. We uncovered the clandestine historical figures who mapped this territory centuries early. And we use the fundamental theorem of arithmetic to extract the chemical formulas of numbers to synchronize space and time.
It is a profound shift in perspective. And to leave you with a final mind bender, the textbook offers one last brilliant puzzle in its Work It Out section. It's a biological mystery about cicadas.
Oh, right. Cicadas are those loud insects that stay buried underground for years and then emerge all at once in massive, overwhelming swarms.
Yes. And biologists noticed something incredible. Their life cycles are almost exclusively 13 years or 17 years. Both of those are prime numbers. The textbook asks us to consider this from an evolutionary perspective. Think about how common multiples work with prime numbers. If a predator has, say, a 2-year or 4-year life cycle, why would evolving a prime number life cycle be a massive biological advantage for the cicada?
Wow, okay. Think about the mechanics of the least common multiple we just talked about. Imagine a predator that eats cicadas has a population boom every 4 years. The cicada is on a 17-year cycle. When do those cycles overlap?
17 times 4 is 68. The predator will only experience a synchronized boom with the cicada every 68 years.
But imagine if the cicada hadn't evolved a prime number cycle. Imagine if they were on a 16-year cycle. The least common multiple of 16 and 4 is 16. The predator would have a massive population boom at the exact same time the cicadas emerge, every single generation. It would be an absolute massacre.
Exactly. By utilizing a prime number, the cicada ensures its lowest possible mathematical overlap with any potential predator cycle. It is literal evolutionary cryptography.
They are using the exact same mathematical principles to protect their species that your bank uses to protect your credit card.
Isn't that amazing? Look closely at the numbers around you. They aren't just counting tools. They are the elemental code of the world, keeping everything a lot more secure and synchronized than you ever realized.
I definitely encourage you to ponder that evolutionary math puzzle on your own.
Thank you for joining us on this deep dive into Section 3.1. We will see you next time.